Hello, math learners! Our lesson for today is about graphing polynomial functions. The learning objectives are: you are going to determine the behavior of the graph, find the upper and the lower bounds of zeros, construct the table of values, identify the zeros and y-intercept of the polynomial function, determine the number of turning points, and sketch the graph of polynomial functions. Let us have examples. You are asked to graph each polynomial function. Here are the steps in graphing polynomial functions. First, you have to describe the behavior of the graph, determine the upper and the lower bound of zeros, construct the table of values, identify the zeros and y-intercept of the polynomial function, determine the number of turning points, and you have to sketch the graph. Let us have number 1. If you are asked to graph the polynomial function f of x is equal to x cubed minus 4x squared minus 4x plus 16. Step 1 is to describe the behavior of the graph. The polynomial function is of the third degree, which is odd, and its leading coefficient is positive. Then, the extreme left and the right parts of the graph are increasing. For step 2, determine the upper and the lower bounds of zeros of the given function. For the upper bound, let us have c is equal to 5. And let us identify the numerical coefficients of the given function. First, we have 1, negative 4, negative 4, and then 16. The value of c is 5. And then we have to use the synthetic division. Bring down 1. 1 times 5 is 5. Negative 4 and 5 is 1. Then 1 times 5 is 5. Combine negative 4 and 5 is 1. And 1 times 5 is 5. And 16 plus 5 is 21. This will mean that 5 is the smallest integral upper bound. You knew already how to solve for the upper bound. Just take note to determine the smallest integral upper bound. Start testing c is equal to 1 to any positive integer wherein the resulting quotients and remainder are positive or may contain 0. So they are all positive. Next, for the lower bound, let us have c is equal to negative 3. And identifying the numerical coefficients of the function, we have 1, negative 4, negative 4, and 16. And the value of c is negative 3. And using synthetic division, then bring down 1. 1 times negative 3 is negative 3. Combine negative 4 and negative 3, it's negative 7. And negative 7 times negative 3 is positive 21. Combine negative 4 and 21, the result is 17. 17 times negative 3, then you have negative 51. Combine 16 and negative 51, then you will have negative 35. So, negative 3 is the largest integral lower bound. So again, just take note to determine the largest integral lower bound. Start testing c is equal to negative 1 to any negative integer wherein the resulting quotients and remainder form alternating signs. So you have positive, negative, positive, negative. Next, you have to construct the table of values. you can start with the lower bound, which is negative 3. The result is negative 35. Then you can use negative 2. The result is 0. Negative 1, 15. Then you can use negative 0.5, which is equivalent to 16 point something, or you can round off to 17. 0 is 16, 1 is 9, 2 is 0, 3 is negative 5, 4 is 0, and 5, this is the upper bound. The result is 21. To find the value of f of x, simply substitute the value of x to the given polynomial function. For example, x equivalent to negative 3. So, you have to substitute negative 3 to x, and you take the cube. Here, change x to negative 3, and then you square. And then, negative 3 to x. And then, simplify. So, you have negative 27, negative 36, positive 12, positive 16. Which will give you a result of negative 35. That is why it's negative 35 here. For the other solutions, you can do it yourself. Next, identify the zeros and the y-intercept of the polynomial function. So, the zeros of the polynomial function are found from the table of values. And the zeros are negative 2, 2, and 4, and they are also called the x-intercepts. The result of f of x when you substitute x to the function is 0. So there are 3 zeros in the given function. And the y-intercept is 16 with the coordinate 0, 16. If you will substitute 0 to every x in the polynomial, the result is 16. Or simply take the value of the constant, and that is the value of the y-intercept. Step 5. Determine the number of turning points of the given function. A turning point is a point of the graph where the graph changes from increasing to decreasing, meaning rising to falling, or decreasing to increasing, falling to rising. A polynomial of degree n will have at most n-1 turning points. The polynomial function is on the third degree. Thus, the number of turning point is 3 minus 1, which is equal to 2. Next step, sketch the graph of the function f of x is equal to x cubed minus 4x squared minus 4x plus 16. So first, let us have the behavior of the graph, in which the extreme left and right parts of the graph are increasing. Then, the upper bound is 5 and the lower bound is negative 3. Next, the table of values started with negative 3 as the lower bound, going to positive 5, that's the upper bound. And identifying the zeros, it's negative 2, it's here, the value of f of x is 0, and then positive 2, so again, the value of f of x is 0. And then 4, so look at 4 here, the value of f of x is 0. That is why we call them as zeros of the function. And the y-intercept, when the value of x is 0, the result is 16. So it's 16 there. And it is also the value of the constant. And the number of turning points is 2. That is 3 minus 1. It's 2. Then we have to sketch the graph. So all you have to do is to plot the points. So first, we have negative 3, negative 35, negative 2, 0, negative 1, 15, negative 0.517, 0 and 16, 1 and 9, 2, 0, 3, negative 5, 4, 0, and then connect with a smooth curve. Do not forget to label the graph properly with the y for y-axis, x for the x-axis, and you place arrowheads because the graph is increasing. If the form of the graph is like this, it will mean extreme left and right parts of the graph are increasing. Next, you have to take note that you can use the points from the table of values to graph the polynomial function. We may use a greater interval or any number if there are larger values of y coordinate. Like this, I use an interval of 10. So from 0 to negative 10, negative 20, you have there 10, 20, and going up, that's 10, 20. Here, going down, 0, negative 10, negative 20, negative 30. Because the value of y is negative 35 and the value of y here is positive 21. After plotting the points, start connecting the points from the lower bound to the upper bound or simply from left to right. So you can start here, connect with a smooth curve, and there, going down, then there. And notice there are two turning points. And make sure it is a smooth curve upon reaching the turning point and label all points. Example number 2, you have to graph f of x is equal to negative x cubed plus 7x minus 6. Step 1, describe the behavior of the graph. So the polynomial function is of the third degree, which is odd, and its leading coefficient is negative. Then, the extreme left and right parts of the graph are decreasing. For step 2, determine the upper and the lower bounds of zeros of the given function. For the upper bound, we can have c is equal to 3. Then, identifying the coefficients of the function, we have negative 1. Then, the exponent here is 3, so we need to replace 0 for exponent 2. So next to negative 1 is 0. Then you write 7 followed by negative 6. And c is positive 3. Applying the synthetic division, you bring down negative 1. The negative 1 times 3 is negative 3. Combine the two, it's negative 3. Negative 3 times 3, it's negative 9. Combine the two, you have negative 2. And negative 2 times 3, we have negative 6. Combine the two, then we have negative 12. Therefore, 3 is the smallest integral upper bound. You have to take note, if the leading coefficient is negative, then the resulting quotients and remainder are negative to determine the smallest integral upper bound. So they are all negative. Next, for the lower bound, c is equal to negative 4. Then, identifying the coefficients of the function, we have negative 1. Then, replace 0 for the missing term. Then, we have 7 and negative 6. And c is negative 4. Then, using the synthetic division, you bring down negative 1. Negative 1 times negative 4 is positive 4. Combine, it's 4. And 4 times negative 4, it's negative 16. Combine, the result is negative 9. Negative 9 times negative 4, the result is positive 36. Combine, the result is 30. Therefore, negative 4 is the largest integral lower bound. And they have alternating signs. For step 3, construct the table of values. And this is the table of values, starting negative 4 for the lower bound and positive 3 as the upper bound, including the zeros as well as the turning points with the y-intercept. Let us have one example at x is equal to 3. Given the function, substitute 3 That's negative 3 cubed plus 7 times 3 minus 6. Then this is negative 27. This is positive 21 minus 6. And the result is negative 12. That is why when the value is 3, the result is negative 12. For the other solutions, you can do it yourself. Next, you have to identify the zeros and the y-intercept of the polynomial function. The zeros are negative 3, 1, and 2. The values of f of x of these numbers will give you 0. And they're also called the x-intercepts. The y-intercept is negative 6 with the coordinate 0, negative 6. Or just simply look at the constant, and that is the y-intercept. Next, step 5. Determine the number of turning points of the given function. Since the polynomial function is on the third degree, the number of turning points is 3 minus 1, which is 2. The importance of determining the coordinates of the turning points is to know the height of the curve. Take note, this is only applicable if there are 2 or more consecutive same values of y coordinates. First turning point. The points with the same y coordinates are the points with coordinates negative 2 and negative 12, and the point with coordinates negative 1 and negative 12. So to find the x-coordinate of the turning point, represented by x sub tp for turning point, we will use the formula x sub tp is equal to x sub 1 plus x sub 2 over 2. Then, you substitute negative 2 to x sub 1 and negative 1 to x sub 2. There. This is the value of x sub 1 and this is the value of x sub 2. And then divided by 2, the result is negative 3 over 2 or negative 1.5. To find the y-coordinate of the turning point represented by y sub tp for turning point, use the value of the x-coordinate turning point and substitute it to the given polynomial function. That is, y sub tp is equal to, the value of x here is negative 1.5, substitute to the function, and then take the cube, 7 times negative 1.5 minus 6. And the result is negative 13.13. Thus, the first turning point is at point with coordinates negative 1.5 and negative 13.13. For the second turning point, the points with the same y coordinates are 1, 0, and 2, 0. So, solving for the value of x, that is 1 plus 2 divided by 2, that is 3 halves, or 1.5. And for the value of y of the turning point, you have to substitute 1.5, take the cube, then change x here with 1.5 minus 6 is equivalent to 1.13. Thus, the second turning point having coordinates 1.5 and 1.13. Next, you have to sketch the graph of the given function. Let us have now the behavior of the graph, which is extreme left and right parts of the graph are decreasing. The upper bound that we had is 3 and the lower bound is negative 4. Then the table of values starting negative 4 for the lower bound and positive 3 for the upper bound. And we had already the zeros here, negative 3, intercept negative 6. And we included already the turning points. Then the number of turning points is 2. And let us sketch the graph now. Let us plot the points now. So we have negative 4, 30, negative 3, 0, negative 2, negative 12, negative 1.5, negative 13, 13, negative 1, negative 12, 0, negative 6, 1, 0, 1.5, 1.13, 2, 0, and the point with coordinates 3, negative 12. And then connect with a slight curve. And do not forget to place arrowheads here and here. Label with Y and X, and also the coordinates of the points. You can start from here, going down. This is the first turning point. Then we have here the y-intercept. We have the second 0, then the second turning point, the third 0 of the function, and the last is containing the upper bound. So if the manner of the graph is like this, the behavior is extreme left and right parts of the graph are decreasing.